Hi, my name is Daniel Retzer. I'm a senior engine programmer at Funcom Oslo. I've been working with Funcom since 2008, and I've been mostly involved on MMORPGs and large-scale open-world survival games. And for these type of games, game logic can often become a bottleneck. This usually stems from being written in a single-threaded manner and basically not designed with cache coherency in mind. So moving forward, we kind of wanted to improve on that. And we basically wanted engine level performance even for game logic. So ideally, we want our performance captures to look less like that and look much more like that. But let's have a look at Unreal ticking in the first place. Unreal ticks would usually be issued on game thread. And basically, an actor tick function would read different dependencies, which could reside anywhere in memory and are hard to quantify and hard to track. But basically, they would just read from dependencies, receive the data, massage it, read from different dependencies, and do this over and over again. Once the tick function would finish, it might pick up another tick task that was ready and would do it all over again. But it might not be the same tick. It could be a different tick function altogether, which obviously is bad for instruction cache performance. So how would we like it to work? Ideally, we want to have logic to be run on prefetched inputs. So basically, we would have already laid out data. We would read from that. And depending on some parameters, we would just spawn batches of workloads that would basically run ideally on all worker threads. And once finished, they would produce an output, just right back somewhere. And this might be waterfalled into different processors. So a processor might pick up the outputs of a prior processor and basically continue. And it could be any kind of number of processors being involved. So how did we go about this? We based our framework that we wrote on ECS, which is short for Entity Component System. If you're interested in how ECS works, there's a nice presentation from Overwatch, which I can recommend watching. ECS in itself basically favors composition over inheritance and has data orientation in mind, which lends itself pretty nice to our own framework. The framework we wrote is basically, we just call it FGL for fast game logic, which I'll be referring to from here on. But we have a nice twist added to it, because we wanted to tackle the single-threaded nature of game logic by getting automatic parallelization. Obviously, we're trying to still keep thread safety. Components in our framework are just U-structs. We decoupled all logic, and they're just PODs. And they're usually small in size and are allocated in contiguous memory. So each component pool would have a blob of memory just for this component type. The logic being decoupled from the data would then run on batches of components. And this logic basically, and we would call processors to have a different name than system, as ECS would call it. System is reused all over in the code base, so it's nice to have a bit more clear name for it. And that way, basically, we would utilize the instruction cache and data cache as best as we can. But maybe we should just first look at an existing project that we had to get an idea of which parts are costly. Let's look at Conan Exiles. Conan Exiles was our first Unreal 4 large-scale project. It's a multiplayer survival game and has lots of different gameplay mechanics. Crafting, harvesting, as you can see here, combat and sieging. Player-controlled building is one of the biggest aspects, which is hard to predict because players go insane when they basically build bases. This just gives you an idea of what bases look like in the game. It's tons and tons of building pieces, and they fill the bases with crafting machines, NPCs that guard the bases, lots of logic basically that is associated with those. So this means the world simulation cost around players is really huge on dedicated servers, or if you're playing local play, even there as well. Most of the game logic is run in game thread, and all of the gameplay related data is stored on the actors and their corresponding actor components. Obviously, this yields relatively bad cache coherency, as ticking basically jumps all over the place, and the results can be measured. This was hurting us most on dedicated servers and the current gen consoles, as those have really slow cores. There are quite a few cores, but they're not really fast. Our initial idea was to fix this by implementing tick task aggregation, as we've seen on a presentation from Rare. And it did reduce instruction cache misses, but it didn't address the data cache issues we were seeing, and it didn't help us to utilize more cores. So it was obviously not enough. When we look at one of the things that hurts us was property initialization when we spawned actors. Basically, one player pawn in Conan Exiles consists of roughly 70 components, and we basically spend 0.8 milliseconds just in register component calls, which is quite hefty. If you're targeting 30 FPS, that is 2.4% of the budget. And a regular humanoid NPC would take 0.25 milliseconds, still a considerable amount. And there's more issues, like if most of the game logic and game data is lives on U objects, it puts more strain on the garbage collector. Basically, when we look at our servers, like a moderately populated server with 25 players would take 400 milliseconds just to do the reachability analysis in garbage collection. Obviously, Unreal supports clustering, which makes it much better, but it's kind of difficult to set up and get right. So, as you can see, this needs to be addressed in one way or another. So our FGL components, as I said, were pods, and they were small in size and U structs. In this sample, the M position and M velocity could as well be U properties. So we could use serialization and stuff for that. In this sample, I didn't do that, but it doesn't matter here. If you see, there is a macro, the FGL declare component macro, which basically creates the corresponding component pool, where basically the memory for the components is in one huge blob, basically. Entities in FGL are just UN32 identifiers. And basically, here in this, I'm just highlighting the deferred context, which is basically a context for accessing component pools. And basically here you can see where we want to access the movement component, the combat component, and the honor component. The create call will just create the entity, and we have different commands for assigning components, removing components, and basically here in this case we're just creating the moving component, common component, and honor component, and assign it to this entity we just created. But this is all hunky-dory, but how basically the gameplay programmers are interested in working on sets of objects, and they need a way to find the entities they care about that have the components they care about. So basically we introduced the concept of views, and as I said, they basically just find entities and components. And if the same view is reused in several times a frame, it uses the same results and caches them in some local memory, so that the pointers to all of the components are easy to read. Views, basically, if the component pools, underlying component pools, get modified throughout the frame, then basically the cache data will reflect that the time is being used. They get updated internally. And views, it give you the means to iterate over all of those by having a for each function, which takes lambda which will basically have the signature that you requested, as in, okay, in this case, we want the damage dealer component and the movement component. So for each signature, we'll have an entity ID plus a reference to those two components. And this was pretty good already, but gameplay programmers really wanted to have more fine-grained control of which entities would be included in those views. So I introduced the concept of tags, which are just uint32, and were used usually as bit flags. So if you have a look at this view, for example, this view would basically include all combat components, but it would filter the result by only including the ones that have the alive tag set or specified for those. And this way, basically, you can just filter subsets of those. And there's even more ways of filtering. Basically, if you look at this one, that's the ground vehicle view. It includes all vehicle components and excludes, but it excludes basically entities that would have a flying vehicle component at the same time to basically only get the ground vehicle components in this case. The difference between get, include, and exclude is basically get would basically include the component to be resolved in the for each function as a parameter, while include and exclude will just be included for the filtering, but not for actually operating on the data. So just a filtering mechanism. So processors. Processors are where the game logic is written, and they are just functions that operate on groups of components. It's basically the equivalent of what ECS would call a system. We just didn't like the term system as it's abstract and it's used all over the place. So we just went for processors instead. One of the main goals of FGL is to scale game logic across all cores. And we didn't want the programmers to have to deal with the nitty-gritty details of threading. They shouldn't have to care about synchronization, race conditions, cache invalidation, and the likes. So how can we do this automatically? Well, luckily, that isn't too difficult. Since all of the processors are required to run on FGL components in the first place, the programmers only have to specify an access pattern to indicate which components are read from and which components are written to. That, in conjunction with some batching parameters and supplied thread affinity, gives the scheduler enough information to issue the processors. The very same access pattern is then as well used to limit access to the component data. And that way we can scale without compromising thread safety. So yeah, reads basically produce no contention and can overlap. They can be batched. And if they're used for views, they only allow for const references to the component data. Writes, on the other hand, produce contention. They can't overlap. That means basically only one processor at a given time can be issued locking the specific component. So, I mean, there can be still writes overlap if they touch different components, but if the same component type is contended, no other writes will be issued. And they allow for non-const reference access when used through views. The threaded writes are a kind of special case, so I won't go into much detail, but I can just give a brief overview. Basically, we introduced those to basically allow for overlapping writes, and they do so by either using atomic operations or by only accessing thread local component data. So we might have a component which has pre-allocated copies for each worker thread, and then we would just index from whichever thread we work on. So that's why we can basically have no contention on the actual data. And then often we would have a different processor that picks up the results and merges the results in a sense. So how would processors look like? Let's have a look at one damage processor. This processor basically, as you can see, specifies a read from the movement component. It specifies read from a damage dealer component, and it has some threaded writes on deferred actions component. And this is all that is needed to basically schedule this processor. The processor function basically would look like this. And this damager processor, here you can tell it receives a context. This context basically, the processor will spawn tasks depending on some batching parameters that we give. So you have one damage processor function run per batch, and this can be run on different threads. And the context is basically individual for each of the threads. And so the for each function on this context would basically only iterate on the batch associated for this current task. And that way we are kind of safe in not touching data that is outside of our current batch. And we disallow write access to component outside of the view, outside of the batch data. Yeah, and this way we can guarantee thread safety within there. As I was mentioning earlier, the for each function then basically accepts entity ID, the const a reference to the damage dealer component because that was read accessed. It wouldn't compile if you tried to do something else than const here. And the same for the movement component. And then basically the processor function would just run some logic to read from those components. So once we have a processor, we just need to schedule it. We do so by using the fprocessor registry. We have one of those per tick group in order to make it easier to integrate with existing gameplay systems. And let's have a look at the registration call here. Fdamage processor is the processor we just looked at a couple of seconds ago. And here we basically registered on the prephysics registry, and then basically have a static identifier Fdamage processor. The static name macro you see, all it does is it hashifies the supplied string and then uses this to fill a fstatic name structure. Fstatic names are mirroring what fname do, just the, instead of relying on runtime indices, it uses the static hash. And the next step would be to supply a lambda which accepts the context for each of the batches that are spawned from the scheduler. These we just forward to the damage processor function that we defined earlier, and that one needed as well a deferred actions component. This is a singleton component, which I haven't mentioned before, I think. Singleton components we use for passing global data into different processors, so it can be used in different stages. But in this case, it's a threaded component, which basically creates an instance of the component per worker thread. So we can, without contention, write to those components from each individual thread. And then we only have to merge the result at a later stage. The next thing would be the minimum batch size. Usually the programmer would just leave it at default. But if we have, for example, processors which are of very simple algorithmic complexity, it might be useful to tweak this value up in order to compensate or basically the overhead of spawning more tasks might not be worth it. So here we can basically just tweak the values to match the complexity. But again, usually just leave it at default. And then we're only missing the thread affinity. In this case, we specified any thread in order to basically make use of all of the worker threads that are available. So let's look at Unreal Insights. I basically added tracks that would show contention on the different components being locked, and it would show which locking type there is. If it's a read locked, write locked, or thread write locked. So here you can see I'm trying to highlight. It's a bit narrow, so it's hard to see. But in this stage, the movement component is write locked, and the processor that you see at the bottom, it's a small purple or pink processor. This one just writes, does the movement logic and updates the positional data in the movement component. Then we have a different processor, which, or it's actually two processors run. You can see an update Unreal movement processor, and there is a spatial hash map processor. and they have different locking patterns. But yeah, you can see they can run in parallel, and they touch different components. So in total, we have the owner component being read from, a movement component being read from, a combat component being written to, and a spatial hash component being written to. This was the update unreal movement processor I was mentioning earlier. And this one is the spatial hash map processor I was mentioning earlier. So let's have a look which of the ones are touching what data. So the update unreal movement processor would read from the owner component and movement components and would basically write back to the unreal objects, to the actors. So basically the movement data was generated by an earlier processor, and now it's getting written back to. And the spatial hash map processor reads from the same movement component, but will write to the combat component and to the spatial hash component. And yeah, that's basically it. You can see here later on we have two different processors that run here. That is a healing processor and a damage processor, and they can overlap with most of the other processors. So they fill up all of the worker threads, which is nice to see. This is what we want. This is basically Unreal Insights captures that I did from an exercise, which I will go into detail later on. So just had to briefly look at this here. So let's look at how do we interact with the component pools. The component pools are either accessed in immediate mode through an immediate context, and the immediate context basically takes the same access pattern that we would define on processors. So basically read or write. And it would be used to limit access to the components so that basically we prevent some programmers from basically telling the processor to run read access, but then trying to get the write access would just not compile. And this is basically an extra safety mechanism to ensure thread safety. Otherwise, people would maybe exploit the system. And it would be hard to track down if someone said, yeah, use read access, but actually does modify data inside. So yeah, the immediate context basically give direct access to the component pools and give you either, in the read case, const access to the component data, or it allows you to read from the tags for each of the components. In the write case, it would allow you to basically get non-const reference to the component data, and it would allow to modify the tags. And it allows you to assign and remove components immediately. And we introduced a different context, which is a deferred context. They don't lock the component pools, but are great for basically just assigning components that you don't need immediately, but they will show up after either you can introduce a specific flush to get those components being created when you need them, or you can just rely on a at the end of frame flush that automatically happens, and then the changes will be visible next frame. So it's kind of dependent on how you want to use it. But yeah, basically a deferred context, when it's created, creates a transaction for each of the touch component pools. And then basically you can, on this context, record all of the modifications you want to do, like assign new components, change the tags. And once the deferred context goes out of scope, all of the transactions get committed to the pool. Committed means they are recorded in the pool, but they're not written yet. So the changes aren't visible until a flush happens. And the flush will basically respect the order in which the transactions are created to have some sort of control of the order of execution here. And yeah, so either the flush is going to happen at the end of frame if you don't care that the components are needed this very frame, or if you need it for a specific processor, you could introduce a processor that flushes those changes. So, like I mentioned earlier, the exercise we had was initially just a proof of concept, where basically I wanted to figure out, does this work? Or does it work as we intended? But later on, we found out that this is a good test case to basically onboard new programmers to get used to this framework. So let's have a look. The sample is really simple. I mean, basically, there's three different kinds of three different kinds of actors. There's passive ones, which basically just fly in random directions and would basically reflect off the level bounds. Then we have a healer. The healer basically just extends on passive, and it basically has some AoE healing around each of those healers. And it's implemented super naive. It will just basically iterate over all entities and basically do a radius check in order to find out which ones then need to be healed. And then basically we have damage dealers, which do the exact opposite. And my test machine is a Ryzen 2700X. And let me show you a quick video of how this looks like. So you see the different kinds of actors here, represented by different colors. Those are the healers. This is the damage dealers, and then you have the passive ones. And yeah, eventually some of them will die because of the damage processors damaging the stuff around them. And yeah, the healers will try to keep that from happening. So let's have a quick look. When we basically just ran this with our standard Unreal ticking, which basically did what I was mentioning earlier, just iterate over all of them, apply a radius check, and apply some health modification. The simulation would take 6.8 seconds. Obviously, this is not good enough. So how does this look like by using FGL, but just comparing it like to like, still run it single-threaded, but just basically get better cache coherency by having all of the data in the tiny components and have those in contiguous memory. That way we should get much better cache coherency. And the results are pretty mind-blowing, to be honest. We get like a 99% reduction in execution time. So basically now we're sitting at 66.6 milliseconds. And this is basically with no algorithmic changes. And I mean, I guess that's easy to explain because it's a typical O(n) square problem. It has very simple logic, but lots of memory accesses. And the Unreal actors and components being spawned in arbitrary locations in memory yields almost no cache coherency at all. So once we use FGL, we get pretty tremendous speed up by just having so good cache coherency. So later on, we introduced a spatial hash map to basically tackle the O(n) square problem. And this gives us another huge speed up. Here we're basically running at 19.5 milliseconds, but still single-threaded. So basically the last step would be to enable all worker threads and plow through all of the data. At this point, we're running at 6 milliseconds well tick, and we're being bottlenecked actually by the processor, which would write back all of the movement, all of the movement updates, which you can see here is running at 5.2 milliseconds. Improving beyond this point will basically not give us any speed gains anymore. I mean, this is obviously a best case scenario. When you look at real life game systems, they will not scale to the same extent because they have much more intricate logic and will not be as memory bound as this sample is. So how did we integrate this all with Unreal to make it an easy integration? We basically changed the Unreal header tool to support FGL as an extension. So basically, we just apply FGL in the U class specifier, and this would create all of the necessary boilerplate, which basically has a entity ID, setting the entity ID, getting the entity ID. The only thing the game coder needs to do is create or supply functions which do create the FGL state and destroy the FGL state. And that basically looks similar to that. I will just fly over it because we're quite time constrained. So maybe just look at it afterwards. The destroy FGL state does then basically just clean up afterwards. The FGL lifetime is basically tied into the lifetime of the owned U object. But we didn't want to introduce lots of defensive programming. So basically we made sure that actors that are being destroyed within the frame get deferred to the end of frame. That way we basically can have processors run on valid data all the time, and we don't need to do pending kill checks and reduce just the amount of branching in general. Currently, all processors are required to finish within the corresponding tick group. We have future plans to basically extend that so we can span processors over several frames if need be. Whenever processors need to access U objects and their methods, we can't guarantee thread safety for those. So basically we enforce the rule that those need to run on game thread to basically keep thread safety. And RPCs face the same issue, obviously. So basically, our processors are often waterfalled. So basically, we try to do as much broad processing on any thread, and then eventually would have a flush processor, which basically writes back to the game thread to update the actors and actor components where need be. RPCs do it in a similar way, where basically they would record a payload, and then which would just flush this at a later stage on game thread. Reputation is another issue that needed to be addressed. Properties live on the FGL components, no longer on the actors or actor components. And the actor components themselves, they can change location memory because we want to keep our component pools tight. So whenever an entity dies or component gets removed, we basically move the components in order to keep the memory tight. So we needed to address this in a sense that we introduced a proxy object, which does all of the replication for you. So basically, the actor, you introduce a property, which is the proxy property, F replicator, it's called in this case. And this one you would register all the properties it needs to update in the FGL component, and it just relays it at a specific point in the frame. It happens during network tick, which is just before world ticking. There's no other processor work issued there because we only issue processors in regular tick groups. So, blueprints. Blueprints we really wanted to keep, as blueprints really help with early prototyping, and we did so by introducing an FGL tick, which is basically run from its own specialized event graph. And basically those run as well outside, or whenever a tick group finishes, we know that there's basically no outstanding processors running at this point in time, which means we can safely access all of the components from the game thread and won't compromise thread safety at this point. I mean, obviously, this doesn't gain any performance uplift because it's just similar to regular ticking. We have no control as there's no processors running. But at least it's not worse than ticking, which is good. Having a quick look at the specialized event graph, this is how it would look like, basically. I won't go into detail here. You can just check this out later. Same way as you would access any other kind of blueprint stuff. We just extended it so you can get all of the components for a specific entity. You can write back to those if need be. This is basically it. So how did this do for us? Or what was our experience of this? Initially, it kind of means a different way of thinking. People were not used to this. So basically, when we started using FGL, it took some time to get used to it. Basically, no of the FGL components existed yet. Basically meant that it took a bit more time in the beginning to get up and running. Another thing that was difficult was that the framework wasn't finished yet when we started using it for our new upcoming title. And since we had to do some quite drastic interface changes at times, caused major headaches for the game programmers because they constantly needed to readapt. So a huge thank you at the game programmers for putting up with me to basically push through this. But eventually, momentum increased as basically the moment you have the most parts of the components created, it's very easy to extend with new processors, which just read from those components. And you only need to introduce fewer components later on. A nice benefit was that basically the code complexity is a bit more, it's easier to grasp because most of the code lives now centralized with the features and is not as scattered around as you would usually have actor ticks. Basically, each actor would implement the tick itself, and you basically, it would be just scattered around the code base. Another benefit, of course, is that it's much easier to vectorize code. As basically processors already work on batches, it's much easier to go on later on and basically SIMDify whatever needs to be SIMDified. And one of the obvious gains is you get much better scaling for game threads, for game logic, I mean, which is a great plus. So this kind of concludes my slides, and I want to thank you for listening, and obviously the obligatory "we are hiring" slide at the end. If any of I'm going to stay here for a Q&A. If there's more questions afterwards, feel free to send them to fgl@funcom.com. And yes, thank you. Have a nice day.